In the spring of 1936, on the concrete apron of Clover Field in Santa Monica, engineers, airline representatives, and test pilots gathered around an aircraft that looked out of proportion to everything that had flown before it. The machine stood high on its landing gear, its wings stretched wide and heavy, 4 engines hanging beneath it like a declaration rather than a solution. This was the Douglas DC-4E, a prototype built not for war, but for a future that American civil aviation believed was already inevitable. The air smelled of fuel and fresh paint, the Pacific breeze carried sand across the tarmac, and beneath the routine calm of a test program, there was a quiet awareness that the industry had stepped onto uncertain ground, from which retreat would not be simple. By the mid-1930s, the United States possessed the world's most dynamic commercial aviation market. Airlines such as United Airlines, American Airlines, and TWA were no longer experimental ventures, but structured corporations operating under federal regulation, fixed routes, and tight economic margins. Transcontinental air travel had become technically possible, but it remained fragmented, dependent on multiple stops, limited payloads, and narrow safety margins. Every additional passenger, every extra mile of range translated directly into profit or loss. Against this background, the idea of a large 4-engine passenger aircraft was not a fantasy, but a calculated escalation. Fewer stops, higher payload, greater reliability through redundancy, and the promise of turning air travel into a predictable industrial service rather than a heroic enterprise. The responsibility for transforming this expectation into metal fell to Douglas Aircraft Company, already successful with the DC-2 and DC-3. The DC-4E was conceived as a collective project, shaped not only by engineers but by the airlines themselves, each demanding range, speed, pressurization potential, onboard comfort, and safety margins that exceeded existing practice. 4 engines were not chosen for elegance but for necessity, because available power plants lacked the reliability and output to guarantee transcontinental service on fewer units. The aircraft therefore became an accumulation of solutions to problems that had not yet fully revealed themselves. From the beginning, critical technologies lagged behind ambition. Engines were powerful but heavy and maintenance-intensive. Electrical systems were complex and fragile. Landing gear capable of supporting the weight required unprecedented structural mass. Aerodynamic knowledge existed, but the margins were thin, calculations conservative, and real-world behavior uncertain. Each requirement imposed by airlines forced another layer of engineering compensation, another increase in weight, another dependency on systems that had never been proven together in a single airframe. This was not ignorance. The people involved understood precisely how narrow the margin was. The DC-4E was not designed as a safe step forward, but as a deliberate reach beyond established limits, justified by the belief that operational experience would close the gap between theory and practice. The risk was accepted because the market demanded it, and because standing still meant surrendering leadership in civil aviation. As the prototype prepared for its first flights, the question was no longer whether the aircraft could fly, but whether the industry itself was ready for the consequences of pushing so far ahead of its own accumulated experience, a question that would not be answered on the runway, but in everything that followed.
By 1937, inside the Douglas design offices in Santa Monica, the Douglas DC-4E had already ceased to be a single aircraft and had become a system of interdependent compromises. Every major design decision solved one problem while quietly creating 2 others, and the engineering process increasingly resembled balance maintenance rather than optimization. The aircraft was not being refined toward elegance or simplicity, but held together through constant adjustment, as if the structure itself required continuous persuasion to remain viable. The fundamental issue was mass. The 4-engine configuration demanded a wing of unprecedented size and strength, which immediately increased structural weight. That weight required more powerful engines, but available power plants delivered torque and vibration levels that imposed further reinforcement on mounts and airframes. Reinforcement increased mass again, which in turn demanded a landing gear capable of supporting loads far beyond existing standards. The result was an electrically actuated, multi-wheel landing gear system whose complexity reflected the absence of lighter alternatives rather than technical ambition. Each added subsystem increased maintenance demands, inspection intervals, and failure points. The wing itself embodied contradiction. It had to provide lift for a heavy aircraft at relatively low takeoff speeds, yet remain aerodynamically efficient at cruising altitude. To achieve this, the wing incorporated advanced high-lift devices, complex internal structure, and fuel distribution schemes that challenged both manufacturing tolerances and field maintenance. Control systems grew correspondingly elaborate. Manual controls alone could no longer guarantee acceptable handling forces, so hydraulic and electrical assistance was introduced, adding layers of dependency between pilot input and mechanical response. Electrical architecture became a silent driver of risk. Redundancy was demanded by safety logic, but redundancy multiplied wiring, switches, relays, and failure modes. Troubleshooting a fault increasingly required specialized knowledge rather than routine inspection. In isolation, each system functioned. Together, they formed a tightly coupled network in which a minor malfunction could propagate unpredictably. Maintenance access suffered as systems competed for space inside a fuselage that had never been designed for simplicity. What mattered most was that the DC-4E did not possess tolerance for deviation. Weight margins were minimal. Performance calculations assumed ideal operation. Any unplanned increase in mass, drag, or system inefficiency pushed the aircraft outside its intended envelope. Engineers were aware of this fragility, but there was no alternative path forward that met airline expectations with contemporary technology. The aircraft could fly, could be controlled, and could demonstrate impressive technical achievement, but only so long as every component behaved as intended. By the time the prototype entered full testing, the design had reached a state where improvement meant further complication rather than simplification. The DC-4E was no longer a platform for incremental refinement, but a structure balanced at the edge of feasibility, awaiting operational reality to reveal whether this equilibrium could survive sustained use, a question that would soon be answered not in drawings or calculations, but in daily operation.
When the Douglas DC-4E entered its flight test phase in 1938, the aircraft behaved exactly as its designers had predicted and exactly as airline operators feared. It flew, it demonstrated range and payload potential unmatched by any civilian transport of its time, and it revealed, flight after flight, that technical feasibility and operational suitability were not the same category of success. The scene repeated itself across test programs. Engineers focused on measured performance, while pilots and mechanics focused on what happened after the engines were shut down. From the cockpit, the aircraft demanded discipline rather than intuition. Control forces were heavy, response lagged behind input, and procedures required strict adherence to checklists that left little room for improvisation. None of this was catastrophic, but it was cumulative. Airline pilots were not test pilots. They were operators expected to fly multiple sectors per day in variable weather on tight schedules. The DC-4E required attention levels closer to experimental aircraft than to commercial transport. Every flight reinforced the sense that the margin for routine error was thin. On the ground, the aircraft revealed its true cost. Maintenance crews faced systems whose logic was sound on paper, but difficult to service in practice. Electrical faults were time-consuming to trace. Landing gear inspections demanded labor hours incompatible with airline turnaround economics. Engine access was restricted by structure designed to save aerodynamic drag rather than maintenance time. Spare parts inventories expanded, and specialized training became unavoidable.
What had been designed as a leap forward in capability became, in operation, a multiplication of costs. For airline management, the problem was arithmetic. The DC-4E consumed more fuel than projected, required longer maintenance intervals, and reduced dispatch reliability. Its advantages in range and payload could not compensate for aircraft time lost on the ground. The business model of late 1930s civil aviation depended on predictability and frequency, not maximum theoretical performance. An aircraft that flew fewer hours per month erased its own technological advantages through lost revenue. The verdict emerged quietly rather than dramatically. There was no single failure, no crash that condemned the design. Instead, operators concluded that the DC-4E solved problems they could not yet afford to have solved. It was too advanced for the economic environment in which it was supposed to operate. Technical excellence had overshot practical necessity, and without a civilian market willing to absorb its complexity, the aircraft had nowhere to go. As interest faded and production prospects collapsed, the prototype remained intact, functional, and unwanted. The failure was not mechanical, but systemic, a mismatch between ambition and context. What followed was not scrapping, but transfer. And with that transfer, the aircraft would enter an environment where ambition was no longer commercial, but strategic, and where the same unresolved compromises would be tested under far harsher assumptions.
In late 1939, as Europe moved toward open war, the unwanted American prototype quietly changed hands. The Douglas DC-4E was sold not through a public military contract, but through a civilian commercial transaction, routed via trading intermediaries and export licenses that described the aircraft in neutral technical language. Officially, it was a transport machine. In reality, its destination and purpose were already understood by those who authorized the transfer. The buyer was Japan, acting under civilian cover but with direct interest from the Imperial Japanese Navy. Japan's motivation was straightforward and structural. By the end of the 1930s, Japanese aviation doctrine recognized the strategic value of long-range four-engine aircraft, yet domestic industry had no experience designing or operating machines of this class. Japanese manufacturers excelled in lightweight structures and short-range performance, optimized for carrier operations and tactical roles, but lacked exposure to the cumulative problems of large airframes, heavy systems, and long-duration reliability. Developing such experience organically would require years Japan did not believe it possessed. Acquisition appeared cheaper than experimentation. The DC-4E arrived in Japan as an object of intense technical interest. Engineers measured, photographed, disassembled, and documented every accessible component. Structural layouts, wing geometry, control linkages, landing gear mechanisms, and internal systems were recorded with precision. What could be copied in metal was cataloged thoroughly. What could not be transferred so easily was invisible. The sequence of decisions that led to each compromise, the alternatives rejected, the reasons certain limits were accepted rather than solved. The aircraft arrived stripped of its developmental memory. Crucially, the Japanese side did not receive the negative knowledge embedded in the project. They did not inherit the accumulated understanding of why the aircraft was economically unviable for airlines, why its complexity exceeded sustainable maintenance capacity, or why its performance margins collapsed under operational deviation. The machine was observed as a finished artifact, not as a frozen record of unresolved trade-offs. Its flaws appeared as correctable weaknesses rather than structural boundaries. Within naval planning circles, the aircraft was interpreted as proof of concept rather than cautionary example. If the Americans could build such a machine, then Japan could adapt it, strengthen it, militarize it, and extract strategic value from a design that had merely failed commercially. The assumption was that failure had been contextual, not fundamental. That assumption shaped every subsequent decision. As the prototype transitioned from civilian curiosity to military template, the transfer achieved its immediate goal: access to physical form. But it also carried forward every unresolved limitation: now detached from the experience that had defined their significance. The aircraft crossed an ocean intact, but the lessons that mattered most never left the drawing rooms and maintenance hangars where the project had quietly reached its limits.
The transformation of the American prototype into a Japanese military aircraft began as an act of confidence and quickly became an exercise in constraint. The Imperial Navy assigned the project to Nakajima, designating the resulting aircraft as the Nakajima G5N, later named Shinzan, mountain tremor. On paper, the logic appeared sound. A large four-engine airframe already existed. Its size promised range and payload. Its structure appeared adaptable. What followed was an attempt to force a civilian design already operating at the edge of feasibility into a role that demanded even greater margins. Reverse engineering progressed methodically. The basic layout of the DC-4E was preserved: wing plan form, fuselage proportions, landing gear architecture. But the moment the aircraft was redefined as a bomber, the balance collapsed. Military requirements imposed additional structure for bomb bays, defensive armament, crew stations, and reinforcement against combat damage. Every addition increased mass. Unlike the American designers, who had fought weight growth through painful compromise, the Japanese engineers treated weight as a solvable parameter, assuming power and refinement could compensate later. Power never arrived. Suitable Japanese engines in the required class did not exist. The selected Nakajima NK7A Mamoru engines were underdeveloped, unreliable, and underpowered for the airframe they were asked to move. Attempts to strengthen structure and systems only worsened the imbalance. The aircraft became progressively heavier, while available thrust stagnated. Takeoff performance degraded. Climb rate fell below acceptable thresholds. Range projections collapsed under real fuel consumption figures. Systems reliability suffered in parallel. The copied complexity of the original design now interacted with an industrial base less accustomed to maintaining such machines. Manufacturing tolerances, material consistency, and field maintenance experience were insufficient to stabilize a platform with no performance reserve. The aircraft demanded perfection from components that could not deliver it. Minor faults cascaded into mission-ending failures. Flight testing confirmed what calculations had begun to suggest. The G5N was slow, difficult to handle, mechanically fragile, and operationally impractical. The design offered none of the redundancy that four engines were supposed to guarantee, because all four operated near their limits. The aircraft could carry a payload only at the cost of range and achieve range only by sacrificing payload. There was no configuration in which it fulfilled its intended strategic role. What had been copied faithfully was not American success, but American limitation. The DC-4E's narrow margins, once tolerable in experimental civil aviation, became fatal in a military context. The Shinzan was not a flawed execution of a sound idea. It was the logical extension of an already exhausted design space. By the time the program's trajectory became undeniable, the aircraft had proven its central contradiction. Strengthening a system that has no reserve does not make it stronger. It makes its failure more certain.
The end of the Nakajima G5N program arrived without ceremony. By 1943, flight testing had confirmed what internal reports already stated in restrained language. The aircraft could not fulfill its intended role under any realistic operational conditions. Production was halted. Strategic bombing doctrine, briefly imagined as a future capability of the Imperial Japanese Navy, was quietly abandoned. The few completed airframes were stripped of ambition and reassigned as long-range transports, a role they performed reluctantly and inefficiently, burdened by weight, unreliable engines, and maintenance demands that exceeded their limited utility. The project did not fail spectacularly, it simply ceased to matter. This quiet ending stood in contrast to what was happening on the other side of the Pacific. In the United States, the failure of the DC-4E had not been interpreted as proof that large four-engine transports were impractical. Instead, it was treated as data. Engineers and managers extracted specific conclusions. Complexity had to be reduced, systems simplified, maintenance prioritized over theoretical performance. The result was not a refinement of the DC-4E, but a deliberate retreat from its excesses. The later DC-4 and its military derivative, the C-54, abandoned experimental features, reduced system interdependence, and accepted lower theoretical limits in exchange for reliability and scalability. The difference was not technical knowledge alone, but institutional memory. American designers carried forward an understanding of why certain paths had failed and which compromises were unsustainable. The Japanese program, in contrast, began without access to that accumulated negative knowledge. It inherited form without context, structure without history. Decisions that had once been made reluctantly, under constraint, were interpreted as incomplete solutions rather than warnings. The same physical concept therefore produced opposite outcomes. In one system, failure became a filtering mechanism that removed unworkable ideas and preserved viable ones. In the other, failure was replicated because its causes were never fully understood. Engineering experience proved non-transferable in the absence of organizational continuity, economic feedback, and operational learning. The G5N's disappearance left little trace in combat history, but its significance lies elsewhere. It demonstrates that technology is not an object, but a process, and that copying the visible result of that process does not recreate the conditions that made it possible. Without engineering memory, complex systems do not mature, they repeat their own limits.